Alright guys, welcome to this page of the notes. I actually want to start this page of the notes because what we're going to be looking at is function notation. And we're going to start this with a story. I can't remember exactly who the author is. It may have even been Dr. Seuss. And I don't remember the story exactly, but the way the story goes is that there was this older woman who has a lot of children. And she named all of her children Dave. And the problem that she had, or the problem she was having in the story, is that when she wanted one of her children, she would say, "Hey, Dave, come here," and however many children she had would come running. And then throughout the rest of the story, which leads me to believe that it was a Dr. Seuss story, she then at some point in the story says she has wishes, she had named her children, and then he gives you a bunch of names that rhyme. And because the problem she's having is that when she calls for one child, they all come running because they have the exact same name. We want to avoid that problem in math, and here's where that problem can come up. Every time that we write an equation or a function, all right, we don't want to call all of them y. We need to be able to give them different names for the exact same reason. On a quiz or a test, if the directions say, use the function y to blah, 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 whatever it is I ask you to do. Well, if all of the functions are named y, you're going to be like, wait a second, which one do you want me to use? They're all named y. I don't know which one you want. It's the exact same thing. When the old woman calls for Dave, all of her children come running because they're all named Dave. To avoid that problem, we give all of our children different names. That way when I want Josiah, I say, "Hey Josiah, come here." Josiah comes running. Baby Jessie stays where she's at. She knows that she's not needed. We're going to do the exact same thing with functions. That way on a test, when I say to you in the directions, use the function g of t to do blah, 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 whatever I ask you to do, you look at the list and go, oh, he wants me to use this one because it's named g of t. I know which one to use. Now let's talk about, right now we know why it's important to name them something different. We can't call them all y, or we're going to get confused. How does the naming work? Well, remember this. We have a dependent and an independent variable. So let's put that. Independent actually, let me switch them. I want dependent first, then independent. I'm sorry. So this will be the dependent. And then independent. All right, now remember on a graph where each of these goes. The dependent variable is always going to be on the vertical axis. So this will be my vertical axis, right? When I graph, my dependent variable is always going to be on the vertical axis. The independent variable will always be on the horizontal axis. Now, I know that you guys like to call the vertical axis y and the horizontal x, because that way it's always the same, it never changes, and you know exactly what to do. I'm just telling you right now that is not how it's going to go in this class. We will change the name of these axes because we need to be able to change the name of our functions. Let me show you how this works. The independent variable, all right, what's on the horizontal axis. Let's just say, for example, that instead of calling it x, I want the variable on the horizontal axis, my independent variable, to be I. And I'm going to name my vertical axis u. Well, the way this works is because my vertical axis is u, the name of my function is going to be the function u. But because u, the vertical axis, depends on what happens with the horizontal axis, I have to include my independent variable with my dependent variable. And so the name we're going to give the function is the vertical axis u of I. Now I know my vertical axis is u, it is my dependent variable, and my horizontal axis is I, my independent variable. Let me give you an application that's maybe a little bit more applicable. Let's say we're talking about somebody traveling somewhere. Well, whenever you travel somewhere, that always takes time. Time, of course, is the independent, so let's say I make my x-axis, my horizontal axis be s for seconds. Now, in order to travel somewhere, you have to travel a distance, and we like to measure distances in meters. So I'm going to go ahead and make my vertical axis the dependent variable m. Maybe that stands for meters. Well, now when I go ahead and write my function, it's going to be the vertical axis m of s. Right? Because I need to include both my dependent m and my independent s, m of s. What if I wanted to do population? Well, if you're measuring a population, we're always going to be measuring a population over time. Well, time, of course, is independent, so we're going to put independent on the horizontal axis. Let's call it t for time. And since I'm measuring population, I will make my vertical axis p for population. So what would I name my function? Well, I would name it p of t. The dependent variable, and then the variable t, which p is dependent on. So here what I've got for you is a number of different ways that we're going to name our functions. I could just call it y. Absolutely, that's perfectly okay. But if I didn't call it y, f is always going to be the dependent variable. It will represent, right, f of x represents your independent, your vertical axis, your dependent variable. X is going to be your horizontal or your independent variable, right? G of t, that's your vertical. T is your horizontal axis. N of w, that'll be your vertical. W is your horizontal. All right, so if we were to graph these guys out, oh, hang on, I got a little crooked there. For this first one, f of x, well, f of x would be my vertical axis, right? That is f of x, and my horizontal axis would just be x, right? This is my independent variable. Since f depends on x, f of x is my vertical axis. What about the next one? If we had g of t. Well, in this case, g of t would be my vertical axis, g of t. T is my independent variable, so t would go on the horizontal, g of t would go on the vertical because g depends on t, and so on. Now, one other story here when it comes to naming these functions. If you were to go to, let's say, a shelter and you're looking for a new puppy, one of the things they tell you when you go to the shelter and you find that perfect puppy for you, and you say, hey, that's the one I want, let me take it home, and they say, hey, well, this puppy already has the name Harley, we would ask, please keep the same name, right? Whenever you pick up a puppy from the shelter, if it's already been named, they just suggest, please keep the name it already has, and the reason is you don't want to confuse the puppy. They've been calling it that name the entire time the puppy's been at the shelter or wherever he was before that, and if you take it home and call him something else, he's going to get confused and he's going to pee on the floor, and it's going to be a huge mess. The exact same thing is true for functions. If the function has already been named, like this one, I've called this one n of w, please don't change the name. It's going to get confused, it's going to pee on the floor, it's going to be a huge mess. I don't want to clean up that mess. So if the function already has a name, please keep the name that it has been given. But if I ever give you a function and say, hey, name this function, you get to call it whatever you want to, name it after yourself for all I care. All that I care about is if I've already named it, keep the same name. Make sure you keep the same name if it's already been named. Here we go. Let's try a couple of problems. What we've got for you is I've given you a relation. I ask you to determine the domain and range, and I ask you to figure out, does this relation represent a function? Well, the easiest way to do this, because it is in set notation, let's make a map. So here we go. We're going to make a map. Remember, I'm going to put my variable or my domain values, my x values, in increasing order, and I'm not going to put in any of the duplicates. So let's find my smallest value. It looks like my smallest value is a 1. So we're going to have 1. Next would be 2, 5, 6, and 7. I'm going to put a box around those guys, and these are my domain values. Now I'm going to need my range values. I'm going to put them in increasing order. I have 4, 3, 4, 3, and 5. Well, I don't want to repeat any duplicates, so it will be 3, 4, and 5. Put a box around those guys, and that's going to be my range. Now, let's draw our arrows. This will help me figure out, is it a function? 1 goes to 4. 2 goes to 3. 6 goes to 4. I have 5 going to 3. And I have 7 going to 5. All right. Now, in order for it to be a function, it must pass the one-to-one test, which means every single value in the domain must go to one range value. Well, since each of these guys only has one arrow going one spot, yes, we are one-to-one. Which means this is a function. This is a function. And I've answered all the questions I've asked you for in that problem, so let's go ahead and try the next one. All right, in this next one I asked you, the relation is given by, okay, so now we've got an equation instead of a set of ordered pairs. That's okay. I want to know, is the relation a function? All right, we can figure that out. What are the domain and range? I'm sure we'll be able to get that as well. And then, is the relation discrete? Or, well, we can answer that question right away. Whenever you are given an equation, it will always be discrete. So let me go ahead and highlight, or discrete. But whenever you have an equation, it will always be continuous. So let me give you that one. There we go. Continuous. Let's go ahead and figure out whether or not this represents a function. We can do that by setting up a map. So here I go. I'm going to have my x values. Once I get back to my marker. Let me choose some x values. So x and y. And here we go. I'm going to pick the trusty ones, right? I'll have -2, -1, 0, 1, and 2. Now, what are my y values going to be? Well, when I plug in a -2, -2 squared would be 4. 4 times 2 would be 8. And 8 plus 4 would be 12. Okay. What if I did a -1? Well, -1 squared. -1 squared is going to be a 1, times 2 would be 2, plus 4 would be 6. Okay. What about 0? Well, if I plug in a 0, 0 squared would be 0. 0 times 2 would still be 0, and then I add 4, I would get 4. All right, well, those ones are descending order, but at least they're still in order. I could flip them around if I wanted to, but at least they're in some sort of order. And I told you I don't care what order you put them in, so I'm not going to worry about flipping them at this point. If I plug in a +1, well, 1 squared is 1 times 2 would be 2, plus 4 would be 6 again. Well, I already have a 6, so I'm not going to write the duplicate. I'll just leave the 6 I already had, so that one's good. What if I did 2? 2 squared is 4. 4 times 2 would be 8. 8 plus 4, I get 12 again. Let me go ahead and put these guys in a box. There are lots of other values I could pick, but I don't have all day, so we're just going to stop with those ones. And let's go ahead and draw my lines here. So, negative 2, yeah, that goes to 12. What else went to 12? The positive 2. Negative 1 went to 6. What else went to 6? The positive 1 went to 6. And the 0 goes to 4. The question is, of the ones that I have chosen, do any of my domain values go to more than one range value? Well, the answer is no. So we pass the one-to-one test. Which means it is a function. And as far as the domain and range go, remember the domain are all the x values, so I'll just label that one domain. However many values that you do, good enough, they're in your domain. And your range value, well, there you go. Those are the range values that you have chosen so far, however many of them you've got, based on how many x values that you chose. That takes care of all the problems on this page of the notes. Head on over to the next page. We'll take a look at something else. I'll see you there.